All right, in this video, we're going to talk about section 3B, dealing with putting numbers in perspective. So here we'll just study several techniques for putting large or small numbers into a perspective that gives them real meaning. Okay, so here we'll look at writing large and small numbers. Working with large and small numbers is much easier when we write them in a special format known as scientific notation. And here's what scientific notation is. It is a format in which a number is expressed as a number between 1 and 10 multiplied by a power of 10. So here, the number has to be at least 1, but less than 10, and then multiplied by some power of 10. Here's a couple of examples of that. Here we got 6,700,000,000. In scientific notation, you will write that as 6.7 times 10 to the 9th. And the way you do that is this. We put the decimal point behind the very first non-zero number. So that decimal point will be behind the 6. So you're going to have 6.7, which is this part right here. Then it's going to be multiplied by 10 to some power. Well, if I put the decimal point behind the 6, that means I have 3, 6, 9 zeros behind it. That would be the exponent for 10. So 6,700,000,000 in scientific notation would be 6.7 times 10 to the 9th. And then another example would be this, the decimal point with all of these zeros and then 2. That's going to be 2.0 times 10 to the negative 15th power. And in this case, we need to put the decimal point behind the first non-zero digit, which is your 2. So you're going to have 2.0, and then you count. We have to go to the right 15 places. So the exponent is going to be negative. Now, if we went to the left to write in scientific notation, then your exponent would be positive. But here you're going to have 2.0 times 10 to the negative 15th power. Let's look at some examples here dealing with writing large and small numbers here. All right, here we're going to rewrite the following statement using a number in scientific notation. And it says that my new music player has a capacity of 250 gigabytes. And you're to recall that giga means billion. And let's say I want to write this in scientific notation. Well, 250 gigabytes, well, we got the 250. That's going to be multiplied by, and we're told that giga means billion. Now, if you recall back in one of the sections when we were extending unit analysis, which is back in section 2B, the phrase giga in the power of 10 would be 10 to the 9th. Okay, so you might have to review back over those notes or the guided notes I gave you dealing with section 2B to find the prefix giga, which is 10 to the 9th. But 250 is not in scientific notation. Let's write the number 250 in scientific notation by putting the decimal point behind the first non-zero digit, which is the 2. So here, this will be 2.5 times 10. And if I put the decimal point behind the 2, I get 2 digits behind it. So that means the exponent for the 10 would be 2. But still, that has to be multiplied by 10 to the 9th. So I bring that over. Now, when I multiply powers of the same base, we have to add the exponent. So here I bring the 10 down, add 2 plus 9, you'll get 11. So in scientific notation, I will have 2.5 times 10 to the 11th power. Okay. Here's the next example. Number 2. The number of different 6-character passwords that can be made with 26 letters and 10 numerals is approximately 2.2 billion. Well, this part, the 2.2, is a number that is at least 1 but less than 10. Now, the word billion, okay, that represents 10 to the 9th power. That represents 10 to the 9th power. Okay. And it's already in scientific notation, so I don't need to simplify this any further. So in scientific notation, it's going to be exactly 2.2 times 10 to the 9th power. Right. And by the way, if you didn't know that, of course, giga means, in this case, billion, which is, of course, 10 to the 9th. And the other one, I think, million, 10 to the 6th. So do refer to this table back in section 2B in your notes. All right, example 3. The diameter of a certain bacterium is about 0.00008 meters. And I want that number written in scientific notation. Okay, so here's 0.00008. Yeah. Now to write that in scientific notation, I need to put the decimal point behind the very first non-zero number. So that decimal point needs to be behind the 8. So in this case here, I will have 8.0 multiplied by 10. Now I moved the decimal point to the right, so the exponent has to be negative. So here I got 1, 2, 3, 4, 5 digits. So it'll be 10 to the negative 5. So it's 8.0 times 10 to the negative 5th power in scientific notation. Okay. All right, here's another one of these. A large power plant generates 7.5 gigawatts of electric power. And you're told to recall that giga means billion. Well, billion, if we were to write that as the power of 10, going back to this table here, back in section 2B, that's going to be 10 to the 9th. So here's what I'm going to have, 7.5. Well, this is at least 1 but less than 10. Then it's going to be multiplied by 10 to the 9th. And that's all I need to do to that problem there, because it's in scientific notation. Okay. All right, next we'll look at how to approximate with scientific notation. Scientific notation can help us approximate answers without a calculator, like in this example here. We're going to estimate the following quantities without a calculator and then find a more precise result using a calculator if necessary. And then we'll discuss whether the approximation technique worked. Okay, so in this case here, in A, we got 5.2 billion divided by 200. So here I'm going to do an estimate. Let's see, I'm going to round 5.2 billion to 5. And the word billion, if you recall, was 10 to the 9th. And then for the 200, if I write that in scientific notation, the 2 will be here times 10 to the 2nd. Of course, you have to put the decimal point behind the first non-zero digit, which is your 2, and there are 2 numbers behind it. So the exponent for 10 will be 2. So 200 will be 2 times 10 to the 2nd. And here, this is a division problem. So let's divide 5 by 2, that's 2.5, times, bring the 10 over and subtract your exponents for 10. 9 minus 2 would be 7. So my estimate would be 2.5 times 10 to the 7. Now for the precise, here they want a precise result. So here we're going to use that 5.2 billion and write that as 5.2 times 10 to the 9th. As 10 to the 9th represents 1 billion. 200, of course, that was 2. I can write it as 2.0 times 10 to the 2nd. Now 5.2 divided by 2.0 will be 2.6 times 10 to the 9 minus 2, which is 7. So the precise answer will be 2.6 times 10 to the 9th power. All right, and now to answer, the part is discussing whether the approximation technique worked. And in this case, it did work. Okay. So usually they're going to have you answer yes or no. Yes, it did. The approximation technique did work because the approximate answer is close to the exact answer. Here's the approximate answer that's close to this precise answer, close to it. 2.5 is close to 2.6. All right, look at part B. We got 30 million divided by 110,000. Let's find an estimate. Now the 30 million, I'm gonna leave that as 30. Or better yet, let's write this as 30 times 10 to the million, if you recall. Million is going to be 10 to the 6 as a power of 10. But of course, that 30 is not in scientific notation, so I need to put a decimal point behind the 3. So it'll be 3.0 times 10 to the, and there's one number behind that decimal point when I place it there, so it'll be 10 to the 1 times 10 to the 6. So I'll have 3.0 times 10 to the 1 plus 6, which is 7. Okay. So now for that estimate, let's take that 3.0 times 10 to the 7th, divide that by, now 110,000. Let's round 110,000 to 100,000. Now 100,000 is 10 to the 6th power. I mean 10 to the 5th, because it's a 1 with 5 zeros, so it's going to be 10 to the 5th. All right, now, or I can write this as 1 times 10 to the 5th. So when I do 3.0 divided by 1, it'll be 3.0. And then 10 to the 7 minus 5 will be 10 squared. So it'll be 3.0 times 10 to the 2nd. Now for a precise answer. In other words, we want the exact answer. 30 million was 3.0 times 10 to the 7th divided by, now 110,000. If I want that in scientific notation, I have to put the decimal point behind the very first one, so it'll be 1.1. And notice that there are 5 digits behind that decimal point that I placed there. So it'll be 10 to the 5th. So I have 1.1 times 10 to the 5th, we're going to divide that into 3.0 times 10 to the 7. All right, now, when I did this, I had to round to 3 decimal places. Okay, so if I do, okay. So if I do 3.0, let's jump out, divided by 1.1, the 3 decimal places will be 2.727 times 10 to the 7 minus 5, which is 2. And you can see here that the approximation method also worked on this one, because the approximate answer of 3.0 times 10 squared is close to 2.727 times 10 to the second. Okay. All right, in part C, the 7,000 times 5,000, 54,999. All right, for an estimate, I will leave this at 7,000. But for 54,999, that's one away from 55,000. So I'll write it like this. Now let's write this in scientific notation. The 7,000, if I put the decimal point behind the 7, I'll have 7.0 times 10 to the, now putting the decimal point behind the 7 means I have 3 digits behind that decimal point. So it'll be 10 to the third times 55,000 in scientific notation would be this. I put the decimal point behind the first 5, and that will be 5.5 times 10. Putting this decimal point here means I have 1, 2, 3, 4 places, 4 digits to the right. So I got 7.0 times 10 cubed times 5.5 times 10 to the 4th. All right. Now, if I multiply the 7 times 5.5, that would be 38.5 times 10 to the 3 plus 4, which is 7. But of course, 38.5 is not in scientific notation. So this is what I need to do here. Place a decimal point behind this first non-zero number, which is 3. So I have 3.85 times 10 to the, now I move this decimal point 1 place to the left, so it would be a positive 1 times another 10 to the 7. So I have 3.85 times 10 to the 1 plus 7, which is 8. Now you could have just multiplied 7,000 times 55,000 out completely and then take that number and convert it to scientific notation. You'll end up with this 3.85 times 10 to the 8. Okay. Now for the precise answer, that means we take 7,000 times 54,999, and we're going to have to use the calculator for this. And that is the big number that you're going to get. In this case, 384,993,00. In other words, 384,993,000. That's the precise answer. And let's say I want to write this in scientific notation. I need to put the decimal point behind the 3. So it'll be 3.84993 times 10. If I place the decimal point behind the 3, I got 1, 2, 3, 4, 5, 6, 7, 8 numbers behind it. That 8 is going to be your exponent for 10. And also they want this to 3 decimal places. So, well, this part right here, if we round this off to 3 decimal places, it would be 3.85 times 10 to the 8. And as you can see that the approximation technique does work, because the approximate answer is close to that more precise answer. Okay. And with the rounding, it would be the precise answer is the same as the estimate. Okay. All right, next we'll look at giving meaning to numbers. Giving meaning to numbers. Some estimates are useful even if they only get us within a very broad range of an exact value. Okay. Now here, the definition of an order of magnitude estimate specifies a broad range of values, usually within 1 or 2 powers of 10, such as in the 10,000s or in the millions. In ordinary language, we usually indicate the order of magnitude estimate by actually using the word order. So we look at this example here, number 6. Let's say we had this. Could an average person lift the weight of $100 in dimes? And they tell you that a single dime weighs approximately 2.27 grams. And here you have to choose which one would be more appropriate for that problem. We got $100 in dimes. Now, for every $1, you have 10 dimes. So here we have to use what they call unit analysis, like we did in 2B. Because 10 dimes make up $1, so the 10 dimes go in the numerator, the $1 goes in the denominator. So here the unit of dollars cancels out. All right, now we're told that a single dime weighs approximately 2.27 grams. So for every 1 dime, the 1 dime has to go in the denominator, is equivalent to 2.27 grams. That way your dimes divide out. So that means we're going to have 100 times 10 times 2.27 grams. And if you look at your choice of answers, they're looking for the weight that's going to be in pounds. So that's why we have to use this unit analysis here, okay? Now, I know this. The fact that 1 kilogram is going to be 2.205 pounds. We need to convert from grams to kilograms. So that means in this case here, 1 kilogram is 1,000 grams. 1 kilogram is 1,000 grams. So the grams divide out. And then finally, 2.205 pounds is 1 kilogram. So 1 kilogram has the equivalent of 2.205 pounds. Okay. Now, we suggest that you refer to the conversion tables that were discussed in section 2B as well to find out those equivalencies here. So here the kilograms divide out, so the final answer will be in pounds. So here I'm going to have 10 times 10 times I'm sorry, 100 times 10 times 2.27 times 2.205. Now, all of this will be divided by 1,000, which ends up being 5.00535. And this is in pounds. So this is a little bit less than, a little bit over 5 pounds. So the correct answer would be that an average person could lift the weight of $100 in dimes, because the weight of 100 dimes is about 5 pounds. It's a little over 5 pounds, but it's about that much. So it would be this answer choice here. Okay. All right, next we'll look at perspective through comparisons here. Comparisons are particularly useful in dealing with units that are relatively unfamiliar, such as energy units. And in this table that you see here is just a just some selected energy comparisons here. Okay. Then in the homework, you'll be given a table like this with some energy comparisons, and you'll be using that to answer some of the questions here. Like in this example. Here you're going to use the data in the table below to determine how many average candy bars an adult will have to eat to supply the energy needed for 7 hours of running. And you see here, energy released by metabolism of one average candy bar would be 1 times 10 to the 6 joules. And then energy needed for 1 hour of running for an adult would be 4.4 times 10 to the 6 joules. And keep in mind, your energy is in joules here. All right, now let's take a look at this right here. We're talking about 7 hours of running. That's going to be multiplied by the energy needed for 1 hour of running. So for each 1 hour of running, the amount needed in joules is 4.4 times 10 to the 6. So I'm going to put the 4.4 times 10 to the 6 joules here. The 1 hour of running, that goes in the denominator. 1 hour goes in the denominator, because we're going from hours to joules. So that means I need to divide out the hours. And then I'll do 7 times 4.4. That would be 30.8. So it'd be 30.8 times the 10 to the 6 joules. Now, I know it's not written in scientific notation, but for now, I'm not going to write that in scientific notation. So now we need to find out how many average candy bars that the adult would need to eat. So here, the energy needed released by metabolism of an average candy bar is 1 times 10 to the 6. So let's take that 30.8 times 10 to the 6 joules, divide that by 1 times 10 to the 6 joules for 1 bar. Okay. Now, in this case here, your 10 to the 6, that's going to divide out. 30.8 divided by 1 would just be 30.8. And it's actually 30.8 bars. But here they want us to round to the nearest whole number, so let's say 31 bars. So to answer this question here, the adult will need to eat 31 average candy bars. So that's example 7. That's how you'll answer example 7. All right, example 8. Here we're going to use the table to the right to answer the following question. Compare the energy released by fission of 1 kilogram of element B to that released by burning 1 kilogram of element A. And they tell you the energy released by burning 1 kilogram of element A will be 5.8 times 10 to the 8th. And then the energy released by fission of hydrogen in 1 kilogram of element B is 1.8 times 10 to the 13th. All right, in this case here, the fission of 1 kilogram of element B to that released by burning 1 kilogram of element A. So from B to A. So here's B right here. That's 1.8 times 10 to the 13th. And that's divided by the energy released by burning 1 kilogram of element A. That's 5.8 times 10 to the 10th. All right, so if I do 1.8 divided by 5.8, and here I'm going to round this to 2 decimal places, so that will be 0.31. Times 10 to the 13th divided by 10 to the 10th. Here we subtract our exponents. For 10, it will be 10 cubed. Now, of course, that is not in scientific notation, so what you'll need to do there is write 0.31 in scientific notation by moving the decimal point 1 place to the right. So it'd be 3.10 times 10. Since I moved this decimal 1 place to the right, it would be -1 times 10 to the 3rd. And then we got 3.10 times 10 to the -1 plus 3 will be 2. So it'd be 3.10 times 10 to the 2nd. And 10 to the 2nd is 100. So if I do 3.10 times 100, you'll end up with 310. So fission of 1 kilogram of element B releases 310 times as much energy as burning 1 kilogram of element A. Okay. All right, next we'll look at a perspective through scaling. Okay, and if you've seen maps before, usually maps do have a scale to it. Like in this case here, if we were to say this verbally, 1 centimeter is equal to 1 kilometer. Okay, 1 centimeter on the map would represent 1 kilometer in a real life situation. Graphically, it will be this. Okay, and notice at the very bottom, you're going to see this bar that represents what 1 kilogram, 2 kilograms, 3 kilograms is, and so on. And as a ratio, we can say 1 centimeter is equal to 1 kilometer. And that means a scale ratio of 1 to 100,000. Okay. Because you have to think of this from centimeters to kilometers. That's 5 places to the right. I mean, to the left. Because for 1 centimeter, that's going to represent 100,000 centimeters. Because the units in this case have to be the same. And you're going to see that in these examples here that I'll be doing here. In example 9, we want to find the scale ratio for the map described below. 1 millimeter on the map represents 100 meters on the ground. Okay. So here you got 100 meters in this case. Now, let's think about this for a moment. And I like to use this scale right here. Because if you go from meters to millimeters, that's going to be 5 power 10, 10, 100, 1,000. So 1,000 millimeters would be 1 meter. Okay, so for every 1 meter, that's going to go in the denominator. We have 1,000 millimeters. And then your meters divide out. So that'd be 100 times 1,000, which is in this case going to be 100,000. So the scale ratio in this case will be 1 to 100,000. Because the 1 is the millimeter, so the scale ratio has to be the same, millimeters to millimeters. Okay. All right, here's another example here. Find the scale ratio for this following map. An inch on the map represents 12 miles. 1 inch on the map represents 12 miles. All right, so this means this. We need to know that 1 mile is 5,280 feet. We also need to know that 1 foot is 12 inches. So we need to convert 12 miles to how many inches? Okay, so our units are the same. Okay, so 5,280 feet make up 1 mile, so we're going to multiply that by the 1 mile will go in the denominator because we want to get rid of miles and convert that to feet. So it'll be 5,280 feet. And if we divide out the miles, they'll be in feet, but it needs to be converted to inches. Well, since 12 inches is equal to a foot, that 1 foot goes in the denominator and 12 inches goes in the numerator. So the feet divide out. So here I'm going to be multiplying 12 times 5,280 times 12. So that would be 760,320 inches. 760,320 inches. And since we got the inch there, that scale ratio would be 760,320 feet to 1. And finally, this last example deals with unit analysis as well. There are approximately 2.6 million deaths per year in country A. Express this quantity as deaths per minute. Okay, so in this case here, the 2.6 times 10 to the 6, because million means as a power of 10, 10 to the 6. Okay, so let me pull this back up. Million, 10 to the 6. All right, and this is deaths, and I'll just write that word out. per year. That means for every 1 year. Now, there's some things we need to know here. We know 1 year is 365 days. I know 1 day is 24 hours. And 1 hour is 60 minutes. Okay, that's common knowledge there. 1 year is 365 days, 1 day is 24 hours, and 1 hour is 60 minutes. So we're going to convert from years, well, deaths per year to deaths per days, and then to deaths per hours, and then from deaths per minute. So here's our unit analysis. We need to get rid of the year. 1 year goes in the numerator, and there's 365 days. So 365 goes in the denominator. That way the years divide out. And then, of course, 1 day is 24 hours. So next, 1 day has to go in the numerator so we can divide it out. And that's equal to 24 hours. The 24 hours has to go in the denominator. That way your days divide out. And then 1 hour is 60 minutes. So the 1 hour goes in the numerator. 60 minutes goes in the denominator. Hours divide out. So that means our final answer there will be in deaths per minute. Okay. In this case here, so if we figure this whole thing out, let's see, 2.6. Now I'm going to multiply that by, now million is a 1 with 6 zeros. That's 200, that's what 2.6 times 10 to the 6 is, 2,600,000. We're going to divide that by the 365. That would give us that amount. Take that amount, divide that by the 24. That would give us this. Take that and divide that by 60. And I think they want this to 1 decimal place as our answer. So this will end up being 4.9 deaths per minute. So for every minute, there are approximately 4.9 deaths in country A. Okay, so that does conclude this video on section 3B, dealing with putting numbers in perspective. Feel free to contact me if you have any questions about anything presented in this video or the homework in my math lab on this section.